Welcome back, everybody. So we're going to start chapter 6, which is going to be on areas and volumes. 6.1, we're going to start by looking at finding areas of regions between curves, and then we're going to extend that idea to finding volumes, actually, of solid figures that we revolve in the plane. So in this chapter, we're going to extend the applications of definite integrals, which is essentially to start with, if we have two functions, we can find the area between them. So if f and g are two continuous functions, the way we would find the area is going to be to subtract the two areas themselves. So we'll note that the integral from a to b of f of x minus g of x dx would be our integral, since that represents the rectangles that would be formed between them, or the slivers or shapes that we could fit between them. And so that is going to give us the area between the two curves. Now, note we do have to consider this for every portion where the functions are above and below. So note in this example, f of x is strictly greater than g of x on our interval AB. But we can also have functions where the relationship changes between the functions between certain points. So maybe we'll have A, B, and C. So if this is F and this is G, then this portion would be F minus G. But the portion here bounded above by the red graph is going to be g minus f. So we can apply this multiple times as those functions intersect with each other as well. But in general, we can think of the area between as the difference of those two functions along the interval integrated. All right, so we can just formalize it here. So we've got less than or equal to, so a to b, f of x minus g of x dx. So something that's going to be really important for this entire chapter is graphing, and graphing these figures so that we can see where they overlap or underlap. In some cases, we'll have access to calculators to work them out. In some cases, we won't. So definitely make sure to be practicing graphing these curves. And I recommend just graphing these curves for just about every example where the functions are relatively straightforward to graph. So we've got two examples here. The one on top is going to be a quadratic and linear function and how they're bounded. And then the second is going to be a mixture of functions. So we've got a cosine of a quadratic and an exponential. And in this case, it's going to be a little bit harder to know exactly where these curves are bounded between. If it's between 0 and 1, so we'll use a calculator to actually graph that. So if we want to find the area of the region bounded by y is equal to x squared plus 3 and negative x plus 1 between x equals 0 and x equals 1. So we're going to need boundary points given for all of these examples. So x squared plus 3, we'll note, is going to look, like this. So we've got y is equal to x squared plus 3. Now the other graph is 1 minus x. So that is going to look a little bit different. So y is equal to negative x plus 1 is going to look like that. So we can see these graphs actually don't intersect, so we don't need to worry about overlapping regions, and we're interested between x equals 0 and x equals 1. So our region is going to be this little sliver in blue here. So then for our area, we can see that the quadratic is always above the linear. So the area is going to equal the integral from 0 to 1 of x squared plus 3 minus negative x plus 1. And I always put my two functions in parentheses, especially that second function, because you're going to have to distribute that negative. So what we'll end up with is the integral from 0 to 1 of x squared plus 3 plus x minus 1, which we can then simplify to x squared plus x plus 2. And now we can just integrate normally. So we'll get 1/3 x cubed plus 1/2 x squared plus 2x from 0 to 1. So note we don't need to worry about the 1 portion. That's all going to be 0. So we only need to evaluate this at 1. So we'll have 1 cubed plus 1/2 times 1 squared plus 2 times 1, all minus 0. So 1/3 plus 1/2 plus 2 is going to be 2/6 plus 3/6 plus 12/6, which is 17/6. So area is just going to be just smaller than 3. So 2 2/3. All right, so for our second function, so we've got cosine x squared, e to the x squared, x equals 0, and x equals 1. These are going to be functions that we can use our graphing calculators for. So if you have your graphing calculator with you, go ahead and graph both of these functions and set your window between x equals 0 and x equals 1. I will use Desmos to graph these functions. So we've got y is equal to cosine of x squared and our other function is e to the x squared. All right, so we'll want to change our window, of course. So I'll do my window from 0 to 1, and then I will maybe shrink my domain down a little bit. Oops. All right, so we can see here that they are going to meet at 0 and then diverge from each other as they approach 1. And the blue curve is our e to the x squared, and our cosine graph is going to be the bottom curve. So in this case, so again, we've got one curve going up, the other curve going down. So there's no other intersection points. So our area is going to equal the integral from 0 to 1 of e to the x squared minus cosine of x squared. Now, both of these functions are not functions that we can integrate by hand. So we can use a graphing calculator to evaluate this. So let's go ahead. I'll use Desmos, but you can put this into your graphing calculator. So we're going to have the integral from 0 to 1. Now I'm going to change these functions to make it a little bit easier on us. So we'll do f of x and then g of x. All right, so note in my example here, it's going to be g minus f, the way I've named them. And then dx. And so what we end up with is 0.5581275. And we can go on from there. But for AP, you can always round to 3 decimal places. So we'll use 0.558 as our answer. So note, if you see that calc OK on any examples, you can feel free to use your graphing calculator. And you'll notice the only thing you really need to do work-wise for the AP on these examples is set up the integral. So make sure that you write your integral. Don't just put the answer. All right, so Now we're going to look at some other examples. So we'll do 2 non-calculator and 1 with calculator. So our first example is going to be a quadratic and a linear again. So we've got y equals x squared plus 4x plus 3, which we can factor, which can help us graphing it. And then y is equal to x plus 3, which is just a linear function. So we can see here that when we graph these, try to be somewhat accurate. All right, so x plus 3, oops, we're going to want to make this a little bit larger. What we're really interested in is where these functions intersect and which function is above and which is below. So we can see y equals x plus 3 is going to pass through 0, 3, and negative 3, 0. So it'll look something like that. And then our graph x plus 3 times x plus 1 is going to be our quadratic, which we'll note exactly passes through 0, 3, and exactly passes through negative 3, 0. So the graph will continue in either direction. So we can see that our region is going to be the region bounded by the line and parabola. Now our line is the above graph. So the area between them is going to be, note we're from negative 3 to negative 1. Oops, sorry. Negative 3 to 0. Sorry, our 2 intersection points are going to be the boundaries for our integral. So negative 3 to 0 of the line minus the quadratic. So then we can rearrange a little bit. So we'll have a negative x squared, and then we've got x minus 4x is going to be minus 3x, and then 3 minus 3 is just 0. So we'll get negative x squared minus 3x dx. So our antiderivative is going to be negative 1/3 x cubed minus 3 halves x squared from negative 3 to 0. So that's going to give us 0 minus, and then evaluated at negative 3. So we'll have negative 3 cubed is negative 27 minus 3 halves times 9, since negative 3 squared is 9. So we can simplify that to minus, and then 27 divided by 3 is going to be 9 minus 27 divided by 2. So let's see, that's going to be 18 over 2 minus 27 over 2, and then this minus sign will make everything positive. So it looks like we're going to have 9 over 2 as our answer, or 4.5. So again, either one of those is perfectly fine. Something you can also do if you're a little bit unsure about your graph or the accuracy of your graph is if you want to find the intersection points, then you can simply set the equations equal to each other also. So we'll set the line equal to the quadratic, subtract everything over. So note if we subtract 3, the 3's will just cancel. So we're really just subtracting the x, and then we can see clearly that we're going to have x times x plus 3 is equal to 0, which implies x equals negative 3 and 0 are our intersection points, which is exactly correct. So you can always set the equations equal to each other if you want those intersection points. Graphing, however, is going to be really, really important, though, because you still need to figure out what the top function is and what the bottom function is. So note we typically refer to this as top minus bottom. Top minus bottom for these functions of x. We're going to also look at functions of y, but we haven't quite gotten to those yet. All right, so the second example. So now we've got a fourth degree polynomial and a quadratic. So find the area of the region bounded. So for our first function, what we can do first maybe is start with intersections and then look at the graph. So the intersection points are going to be when they're equal to each other. So x to the fourth minus 2x squared equals 2x squared. So if we subtract the 2x squared on the right over to the other side, we'll get x to the fourth minus 4x squared, which have a x squared in common. So we can see that x equals 0 and plus or minus 2 are going to be our intersection points. So that means that we have two separate sets of intersection points at plus or minus 2, as well as at 0. So there's 3 separate intersection points in total. So that means we're going to need multiple integrals, most likely. All right, so let's go ahead and let's factor this one as well. So we've got x squared and x squared minus 2. So these are going to be pretty simple to graph. So for 2x squared, that's just going to be a quadratic, passing through at 0. And then for our x to the fourth minus 2x squared, we can use multiplicities to figure out what the graph looks like. So it's going to be, we know that they intersect at -2 and 2. So we'll just note those are going to be intersection points, and they also intersect at 0. But 0 has multiplicity 2, which means it's going to look like a quadratic there. So then our graph is going to look something like this. And the zeros, of course, here are when x squared minus 2 is equal to 0. So those are going to be at rad 2 and negative rad 2, but we can see from our graph we actually don't need those coordinates because our intersection points are at different values. Now the one thing we can notice though, is that our area is going to equal the integral from -2 to 2. We don't actually have to split up this integral because the blue graph, so 2x squared, is always above the fourth degree polynomial. So it's always going to be blue minus red for the height, so we can just integrate all the way. We could split it if we want to, which we'll discuss in a moment, but it's always going to be 2x squared minus x to the fourth minus 2x squared. So what I'm going to use here is the fact that we have even symmetry for both graphs. So we'll note they're both even, and we're integrating symmetrically. So between -2 and 2 about the x-axis, so the distance is the same on either side. So we can simply actually take one area, let's say this area on the right, and double it. So 2 of those areas are going to be equivalent. And the nice thing about this is that it gets rid of that negative for my antiderivative, so I don't have to worry about sign errors that I might make. All right, so working this out, we're going to get 4x squared minus x to the fourth dx. And now we can evaluate. So we're going to get 4/3 x cubed minus x to the fifth over 5. Evaluated at 0 and 2. And note that 0 is going to be really easy to evaluate. So at 2, we'll have 4/3 times 8 minus x to the fifth is going to be 32 over 5 minus 0. So we're going to have 2. So it looks like we're going to have 32 over 3 minus 32 over 5. So we'll want to work that out maybe on the side here. So our common denominator is going to be 15. So I'll multiply 32 over 3 by 5 over 5. and then 3 over 3. So 5 times 32 is going to be 160. So I'm going to get 160 over 3. I think I could fit it here. Minus 96. Oops, over 15. Minus 96 over 15. So 160 minus 96 is going to be 64 over 15. So this is going to be 128 over 15. So note 64 plus 96 is 160. And again, the graph is going to be super, super important, but starting with those intersection points can be really helpful too. All right, so for the last example that we're going to look at, the area of the region between the graphs here is going to be done by calculator. So let's see why that might be. So we've got, let's see, 3x to the third minus x squared minus 10x. And we've got negative x squared minus 2x. So go ahead and put that into your graphing calculator. And then for the window, it's kind of unclear, so I would just do a negative 10 to 10 window for x and y. Just have a nice square window. Good, okay, so you should see the cubic and then the quadratic, and we can see that there's 2 overlapping regions. So I'll draw just kind of a rough sketch here of what my graphing calculator looks like. So we've got something like this, and then our other graph looks something like that, so that our regions are going to be here and here. So clearly it's going to be a little bit messier, but we do have 2 separate regions, and those 2 separate regions are going to be very different. We don't have any symmetry, so we actually do need 2 integrals. So why don't we be slightly careful here and find our intersections. So I'm going to calculate the intersection here on the left. All right, so our first intersection, maybe we'll call that x1, is negative 1.632993. x2 is just 0, since they both pass through the origin. And then x3 it's going to be actually symmetric. Look at that. 3, 2, 9, 9, 3, 2. But the areas are not the same. So we do get actually symmetric distance, but these are not even or odd functions. All right, so we've got those points, which means we can now calculate our area. And we should note this first curve is the x cubed curve, and the blue curve is the negative x squared curve. So maybe we'll give these names. Oh, they did, F and G. Whoops, okay. F and G. All right, so the area then is going to equal the integral from, so we'll do x1 to x2. Note, I've already labeled them. I've given them names. Right, x1, x2, x3. So you don't need to rewrite the numbers unless you really want to, you can. But as long as you have them clearly labeled and named, you can just use the name that you've given them. So we'll have, for our first region, oh, whoops. What am I doing? Let's go back here. That's not the region I want. That's just the region underneath G. The region that I want is up here. Yes, okay. Sorry about that. So those of you who were watching the video earlier and are like, no, that doesn't look right, you are correct. All right, so that is going to be f of x minus g of x plus, and then our second integral will be from x2 to x3, and this is going to be g minus f. And because this is a calculator accessible problem, that's all we really need to write, and then we just need to actually compute the integrals. So let's go ahead and jump out. So there's f and g. So we'll do the integral 0.632993 to 0 of f minus g plus the integral from 0 to 1.632992 g minus f so what we'll get is they are actually the same areas. Look at that. Yeah, so they're actually going to be equal to both equal to 5 1/3, which would be 16/3. So this is going to be equal to 32/3, or 10 2/3. Still not obvious from the graph that they're exactly the same, but they do actually end up being the same. You might get that actually from doing the subtraction between them and kind of seeing where the intersection points are, but obviously these intersections are not obvious values. They are just some irrational quantities. All right. So I think we'll pause here before jumping to functions of y, where we change our orientation here. So if you have questions, shoot me an email. Otherwise, come by the office hours, and until I talk to you next time,